In this video, I'm going to derive the formula for the integrating combinations and show how these formulae can be used to solve differential equations. Let's start with the very first of the four formulae. The first formula, let me write it down here, is written in this way. So this is, I'll start off by writing the four equations. So here's d of uv equals u dv plus v du. And I'll show you that this is nothing but the product rule. Okay. The second equation is d of x squared plus y squared is equal to 2 of x dx plus y dy. Okay? And again, this is, we'll see that this is just a differential, well, it's just a derivative. The third and the fourth are basically the quotient rule, and it just basically goes like this. Dy over x, okay, is given by x dy minus y dx over x squared. And the fourth equation, it's just swap places of x and y. So if I have d of x over y, it's going to be y dx minus x dy over y squared. Okay, so these are the four formulae that we're going to use to solve differential equations. We're going to simplify them. Okay, we're going to take, if you see what's on the right-hand side of these equations in your differential equation, you're going to replace with what's on the left-hand side. Okay, but before we do that, I want to prove to you that these equations work. So the first equation, so we're going to basically derive the equations. Okay, so right now, equation number 1. So if you remember the product rule, it's d by dx of uv. It's u dv by dx plus v du by dx. Okay, and basically all you're doing here to get equation number 1 is by multiplying both sides of this equation by dx. So if I do that, I have d of uv is u dv plus v du. Okay, so that's pretty simple derivation. Now, one thing I wanted to show about this formula is that if you were, so integrate, you know the integration by parts formula? Integration by parts. The product rule, this is just the product rule, but the product rule can be, if you take the integral of both sides of this equation. So you have u duv equals integral of u dv plus v integral of v du. Well, the integral of duv is just uv. Okay, if you have trouble with that, just let z equal uv, and then you have the integral of dz. Okay, well, what's that? That's just z plus c, right? Plus some constant. We can ignore that in this formula. Okay, so we have uv is the integral of u dv plus the integral of v du. So if you want the integration by parts formula, the integral of u dv equals uv, okay, minus, so we're just going to take this integral and bring it to the other side of the equation, v du. And this is your integration by parts formula. Okay, you use this formula when you I want to use integration by parts. Okay? This is just an aside. Okay, cool. Let's take a look at how equation number 2 is derived. So let's look at equation number 2. And we're going to start with the d by dx of x squared plus y squared. Well, what is that? Well, what we can do, that's really just multiply through. So d by dx of x squared plus d by dx of y squared. Well, here we need the chain rule. We need to chain rule. So that is just, well, we know, okay, the derivative of x squared is just, let's say 2x, okay, plus, now, to get the derivative of y squared, we need to say d by dy of y squared by dy by dx. You see how the y's cancel? You see these y's? They would cancel. So you still have d of y squared by dx, just like we have above. Okay, but we've applied the chain rule here. So what's that? Well, we have 2x plus 2y dy by dx, and that is d by dx x squared plus y squared. Okay, great. Now, if we were to multiply both sides of this equation by dx, what we get, these guys cancel, we get d of x squared plus y squared equals 2x dx plus 2y dy, or we can factor out the 2. Okay, and then we can, let me just factor out the 2's here. So we'll put 2, and then we have x dx and y dy. Okay, and this becomes proof. This is our second equation. Let's go, I'm going to go to the next page here, and what we're going to do is derive the equation number 3 and 4. It's basically the same thing. So we have, when you have, let's do this. We have d by dx, and we're saying y over x, right? Well, what's that? Well, that's the same thing as d by dx, okay, of y times 1 over x, okay? And that is, if we apply the product rule, okay, we can, the same product rule that we had above, okay, u dv dx plus v du dx. So this is the same thing as y times d by dx of 1 over x plus the 1 over x times d by dx of y. Okay, so that's actually pretty simple. So the derivative, what is the derivative of x to the negative 1? Let me just rewrite this just to be nice and clear. So this becomes negative x to the negative 2, okay, times y, plus 1 over x dy by dx. Okay, great. So what is this? Well, this is negative y over x squared times 1 over x. So if I want to have the bottom, if I want to have common denominator, I'm just going to multiply top and bottom by x over x. I haven't changed anything. And so the second, this guy is going to become over x squared. So what we have is we have negative y plus x dy all over x squared. Okay? All right, great. And actually, sorry, this is dy by dx, okay? So that is dy dx. And so is this. This is d by dx of y over x. So what I can do is I can multiply both sides of this equation by dx, okay? It'll cancel here. This denominator will cancel and we'll bring the dx in front of the y here. So what we have is we have our negative y dx plus x dy over x squared, and that's just d of y over x. Okay, that's great. So I'm just going to write it in the way that we're used to here. dy over x is equal to x dy minus y dx. Okay, over x squared. Okay, and that's that third formula. Okay, now I don't have to redo this derivation for the third formula because we're just changing places of y and x. So if we have the fourth formula, just make x y and y x. So dx over y is equal to y dx minus x dy over y squared. Same formula, same everything there. Okay. So that's the derivation of the formulae. Okay. The next thing we're going to do is just show an example of how these formulae can be used. Okay, so I'm going to just jump over to probably the more difficult of all examples that we're going to see. Let's take a look at an example of how we would apply this integrating combinations formulae. Okay. So let's check and see. Let me grab an interesting problem, a more difficult problem. Okay, so example. Okay, so let's say that you have this crazy differential equation. So it's x to the 3 plus xy squared plus 2y dx. Okay. And you could say plus y to the 3 plus x squared y plus 2x dy equals 0. Okay, so this is the formula that we have. So what I'm going to do immediately is I'm going to factor out, you see this x to the 3 and this xy squared? I'm going to pull out an x, and I'm going to have an x squared plus y squared. I'll plug in the dx, and then plus 2y dx. Okay? So that's the first half of the equation. Plus, now I'm going to factor out a y from this side. So I'm going to have y, and I say y squared plus x squared. Or actually, let me make it look like this. I have x squared plus y squared on this side. So let me go here and go x squared plus y squared dy plus 2x dy equals 0. Okay, we don't need this guy there. Okay, so now what we can do is we can collect these like terms. So I'm going to grab my x squared plus y squared. Okay, and I have x dx and I have y dy. So x dx plus y dy plus what I have is 2 y dx plus x dy equals 0. All right, do you recognize any of these? Okay, let's go up to here. Let's go up to our formula. And what do I have here? Where did it go? Our equations. We have, so x squared plus y squared, or dx squared plus y squared is 2x dx y dy. Those are the common ones, right? Let me go back down here. X dx y dy, this is literally 1/2. Let me zoom back in. Okay, of dx squared plus y squared. That's literally 1/2 of it. And then we have our x squared plus y squared here. Okay, and then the y dx plus x dy, that's our product rule, right? This is 2 dxy. Okay, that's equation number 1. This one is equation number 2. This one's equation number 1. See, x dx plus y dy is it's 1/2 of x squared plus y squared. And then that equals 0. Okay, great. So now what we can do is we can let's bring the dxy over to the other side of the equation. So I'm going to go like this, -2, and I have my dxy here. And here I have, let me bring the 1/2 out. I've got x squared plus y squared dx squared plus y squared. Okay, now what we want to do is we want to integrate both sides. But this may look difficult or different than what you've seen. Let's simply make a substitution. Let's call x squared plus y squared u. And dxy, okay, I'll call it v, just to make life easy for me. So my equation, so we say let u equal x squared plus y squared, and v equals x, y. And so what I can do is I can just transform this equation into 1/2 u du equals -2 dv. And like we always do, we're going to integrate both sides. And so what does this become? Well, this becomes 1/2 u squared over 2, okay, plus some constant is equal to -2 times v plus some other constant. Okay? And what I'm going to do is I'm going to collect these two constants and bring them over to the other side of the equation. So what I have is 1/4 u squared, okay, is equal to -2v plus, and I'll just collect c1 and c2 into this constant. Okay. Now, if you don't like the 1/4, well, I can just say I can say here u squared. I'll multiply 4 times both sides of the equation. Okay, so I have u squared is -8v plus, okay, 4, I'll call this c naught. Okay, and this I'll just call some constant c. Okay, so my equation, if I sub back in, my u was x squared plus y squared equals 8, and v was xy, -8, xy plus some, oops, I'm going to clean that up a little bit. That c doesn't look that great, plus c. Okay, that's my equation. And that's how you solve this equation. Okay, so the idea is to apply, you're going to go to these 4 equations. Okay, you're going to look for things that are on the right-hand side of the equation. Okay, you're going to look over here. Okay, actually even here too. Okay, and if you see any of these in your equation, you're going to replace them with what's on the left. Okay, and that'll simplify your equation, because when you integrate, it's much simpler. Okay, you like the integral of duv is just uv. Okay, plus c. But all right, so that is the derivation of integrating combinations and an example of a use case for it. Okay, thanks very much, and we'll see you next time in math class.